So the next thing that we're going to talk about today is unit testing. Unit testing is really important in Rosetta because we have all this code and we need some way of making sure that all of it works the way we expect it to. So just a quick overview of what I'm going to talk about today. First, I'm going to go through why it's really important to test your code, and you'll get some experience with this in this lecture. What a unit test is, a philosophy that we call test-driven development. This is where you use testing as a directive for how you want to write your code and defining what it means for that code to be correct. And then finally, we'll do a lab later where you'll write your own unit test for a piece of code that we'll provide to you so you can get some hands-on experience with writing some new unit tests in Rosetta. So the first question I have for all of you is, why do you think it's important to test your code? Don't be shy. Anyone? Yeah? Joe?
Yeah, because there's a lot of developers working on code at the same time, so people can change what you've done and you don't know.
Yeah, that's definitely a really important one. Lots of people are changing the Rosetta code at one time. So unit tests are like insurance. Other people can know if they broke your code, and it sends a flag when you do that. Also, Amanda's answer, knowing what it means for your code to be correct. Anyone else have any thoughts? Whoever's raising your hand. Yeah, that's a great one. Just because your code works in one case, it does not mean that it's going to work for all cases. So you always want to be thinking about not just what does it mean for my code to work in the general case, but what are some boundary cases or edge cases that I might encounter. Anyone else have any thoughts? All right, cool. So you covered the basic ones. Yeah, the first one is how do you know your code is working? Just because the code compiles does not imply that the code would actually run correctly. So a unit test is a good way of figuring out if your methods that you just wrote would work. Next is, let's say you're working on a really large development project. You've written some code, and then you wrote some code out on top of it. A unit test is a good way for you to know if you've broken any of the other methods in your project or have discovered maybe a new edge case that you might not have thought about when you originally wrote the tests. Next, somebody else knows if they broke your code. As Joe mentioned, the Rosetta community is really big. People are committing code pretty frequently. And we actually run the unit tests on a test server anytime somebody commits new code to Rosetta. So what's important about that is somebody else can know if their change might have affected your change. And then finally, it's a good form of formal validation. It forces you to think about what does it not just mean for my code to work on a base case or like the average case, but what it might mean for that code to work on an edge case, something that you might not have thought about or uncovered. And I guess the good analogy for unit tests, it's kind of like your shield. If you're trying to write a lot of code and get it to work, it's kind of like your protection to make sure that you know your code is doing exactly what you want it to do. So what exactly is a unit test? So yesterday, we talked about the idea that Rosetta code is developed in this object-oriented manner, where things are divided into smaller parts so they're more manageable. We can organize them, and those parts can work together. So unit testing is the same philosophy. It's when we break up this giant problem of testing the Rosetta code base into smaller, different pieces. So a unit test is really just this sort of small, boring program. If I have a function that says add two numbers, it just says, like, did I add them correctly? And this is easy to do in object-oriented code because we can sort of write these very small individual tests for each of the objects. So this is sort of an abstraction of like some of the smaller pieces in the Rosetta code base. So you have residues, and you can have like unit tests for residues, or some of the methods in residue, unit tests for some of the methods in atom, and so forth. And I think the best example of, or a pretty solid example of why you might want to unit test individual pieces of whatever you develop in Rosetta instead of just adding a large test for one method is if you think about the ab initio protocol. Say ab initio is about 30,000 lines of code. You're going along, you're doing your experiments, you're on ab initio, and you find a bug. Unfortunately, if you don't write any unit tests, that bug could be on one line of code out of all 30,000 lines of code, and you basically have to find the needle in the haystack. But if you've written individual tests, you can run your test suite. And now you have this much more informed way of figuring out what line of code broke, what do I need to fix, and how am I going to fix it. So it's a much sort of cleaner, easier way to develop and find bugs, because all code has bugs. It's just getting a good way of development for finding them. And so another thing to think about is what it means to write testable code. You can write unit tests for classes, because you can make, I'll show you what a unit test looks like in a couple of minutes. But you can instantiate those classes in a unit test and just kind of call the methods from them. But there are some things that are a little bit more difficult to test in a unit testing way. The first is a pilot app. A pilot app is just an executable. So it would become difficult to call methods in that executable from somewhere else. And then also, it's important to think about not just where you're writing your code, but how you're writing your code. A good way to think about writing unit tests is what are my inputs and what are my outputs. So if you can't fully specify your inputs in the method signature, for example, if you make a bunch of calls like pose.residue, whatever, inside, it's much more difficult to think about what are the set of inputs and outputs that define what it means for that method to be correct. So yeah, so that's sort of the basics of unit testing and why it's really important. But what I want to talk about more is something called test-driven development. So when you write code, you're going to write your code and your unit tests. But there's a philosophy that a lot of people like to use, which is to think about the unit tests before you even start writing your code. This has a couple of benefits. First, it means that as you're writing your code, you're constantly thinking about not just does my code work, but what does it mean for my code to work? It sort of helps you to push boundaries on edge cases, think about all of these sort of individual things that your code could get tripped up on. The next thing that it's really good for is it helps you to write more testable code. If you're thinking about what type of interface you might need to write the unit test, you're more likely to write a method signature that will allow you to sort of test those pairs of inputs and outputs, versus if you sometimes write the code first, you realize you have to change what you wrote so that you can write a unit test for it. So I wanted to sort of give a first example of how you would go through this scenario of thinking about your test cases first on just sort of a toy case, and then we'll go through an example together. So in one of the homeworks, we had you write just a simple calculator. It just added and subtracted numbers. This is kind of the same thing. Write a program that can compute the square root of a number. And let's just say my method just returns a real, so no imaginary numbers here. And then you just compute the square root of that number. So example test cases that you would want to think about when writing this method and made sure that your method behaved correctly on is x greater than 0, x equal to 0, and is x less than 0. If it's less than 0, it should probably throw an error because you only want to return real numbers. So that's just kind of what it would mean to sort of go through the process of what is my method, what does it mean for it to be correct and not correct. So what are the inputs, what are the outputs? So that's just a quick example, but we're now going to go through an example together. So we just talked about graphs. This is a mini social network graph, probably like you'd find on Facebook, Twitter, whatever. And these are all of the BootCamp instructors. So the prompt is write a method where you can find the number of friends that a person has in the network. So in this case, an edge in the graph represents a friendship between two people, and a vertex in the graph represents a person or a friend. So the name of the person is specified in the nodes. And when you're taking a look at this, there are a couple of things that you want to be thinking about. So we just did the graph lecture. Does anybody notice anything in particular? Like, how would you describe this graph? Anyone want? Yeah, it's a tree. Anyone else? Yeah, there are probably not enough nodes to determine that, but yeah, that's fair. Yeah, so taking a look at what you have, like at the graph, will start getting you to think about what are the properties of what I'm working with. Some other important things that I came up with, also some boundary conditions for this exercise. So your network can be any size. So there are 5 people in this network, but there can also be 1 million people in the network. There are no limitations here. Cannot have cycles. Cycles cause some would cause some problems in some types of graph search. Just you can not worry about that for now. And there's no limit on the number of friends. So this issue of like sparse or connected, Jared could have like 1 million friends and I could have one. Like it doesn't matter how many people you're connected to. So now the idea is write a method that could find the number of friends given this graph and given one person. So just using this graph, what are some test cases that you could think about? Anyone? They don't necessarily have to be edge cases, just like general, what's a set of inputs and set of outputs that would help me to know that my method is correct. And don't worry about like the code behind the method, just think about the inputs and outputs. Yeah. So I have one friend, that's a good, what are some other cases? That's good too.
Jerry and Rocco, my friends.
Yep. So what would be, but like for this method, what would be the input and the output? Right, and then what would be the other argument? Like the person? Yeah. So I guess I can sort of, I sort of expand it. So the first case that I thought about, I gave you guys a graph as just an example, but you can kind of expand on it. So the first thing that I thought about is like, what could be my simplest case that I would want to think about if I were to just sort of throw this graph to that method? So if I have a graph size of 1, that means that one person can't have any connections. So your answer should always be 0. The next thing I thought about is, so Andrew was this orange node right here. So if you only look at all of the people 1 edge away or 1 friendship away, he would have 3 friends. And if you looked at all of the people who were 2 edges away, you would have 4 friends. So you can start thinking about it in this way, not just what is the case that's lying in front of me, but what are some possible different cases that I might encounter when I'm testing my code. And basically, if you do this before you write the method, you already have your set of test cases. So when you're writing the code, you can constantly be thinking about, does my code satisfy these test cases? And testing is hopefully becomes a lot easier. So yeah, write the code, write the test cases, and you should really try to only accept code that like meets your test cases, or if you have an edge case and you know about it, document it, and make sure that like you really can't get it to work on that test case for a good reason. So how do you add a unit test to Rosetta? So Rosetta uses a unit testing framework called CxxTest. This is a framework for writing unit tests in C++. Basically what you do is you define a class file, which I'll show you in a couple of seconds, where one class is a suite of tests, and then individual test methods within that class will define individual tests for your piece of code. And what you'll do is when you implement this class, you'll deride it from CxxTest class. That will give you some extra sort of assertion utilities and tools that you can use when you're writing your unit test. And you'll store your unit test in a file called whatever your test name is, .cxxtest.hh. So one thing to note before I show you, so unit tests are unique in where you're sort of defining all of your methods in this one CxxTest.hh file. You're not going to write like a header file and a CC file. It's a little bit different on the testing side. So this is a little bit what a unit test might look like. Or a pretty simple one for the code the example that I just showed you. So here's the class. I called it friend graph test. When you call unit tests, you're going to call them by the name of the class, not the name of the file. And you'll see it inherits from public CxxTest. And then some other differences between a class file that you might normally work with and a unit test is it has 2 special methods. First is a setup method. think about when you're writing a unit test, constructing the graph is something that you'll do before you'll start calling methods on it to figure out its properties. So I could do that in my setup method. And that will run before each test in the test suite. Or I think there's a limit if you have too many tests. And then there's also a teardown method that kind of acts as like your destructor. After you've used your test data, you can sort of clean it up. Usually that's just kind of like a destructor. You don't define methods in it in most cases, though I think there are a few cases in which you might. Some other sort of different properties of the unit test file is that we define test methods using this void test underscore and then whatever the name of your test might be. So if you don't have that part, the unit test suite won't know that it's a test and it won't run it. So that's an unanticipated side effect. If you want to turn off a test, you can just sort of add like a don't test in front of it and the test suite won't run it. But you need that prefix in order to run the test. And then finally, so by deriving your class from CxxTest, you get some testing utilities that are really, really useful. Because if you think about it, a unit test is just making sort of a series of assertions. So if I call this method, what does it equal? These are three really common testing assertions. So the first is TS assert. That's just sort of like your regular assert. If the statement evaluates true, it'll evaluate true. TS assert equals, so you can put two values and it'll assert true if they're equal. And then TS assert delta, that's really useful if you're working with real numbers where you might have some like precision errors you would expect a little bit different. You can give it the two numbers and then by how much they're allowed to deviate. In this case, because I'm working with sizes and I don't expect any differences, I set my delta to 0, but usually if you would use this method, you wouldn't do that. And then there's a lot of other TS assert utilities that you can use. They're all listed on the Rosetta Commons wiki page. There's a whole list of them that are really useful in a lot of different cases. So how do you set up a unit test? There's a really important similarity. You might have experienced this when you did the scavenger hunt. But the Rosetta source directory structure mirrors the test directory structure. That's on purpose. We want it to be so that if you have a test for a particular class, you define it in sort of the mirroring location in the test directory. So if you, let's say you want to define a test for core scoring score function, you'd put that in test core scoring and so forth. And then you can define, as I mentioned earlier, file.cxxtest.hh. And then just as you'd add a file to the build settings, you would do this similarly by adding it to the appropriate test.settings file. And then finally, how do you run a unit test? So we already mentioned you can use scons to build Rosetta. To build a unit test, there's a special additional flag that you'll add on your scons command line, which is cat test. That will build all of the unit tests. And it will behave similarly, where if you only change one unit test after you build all of the tests, it should only build that piece of code. An important difference between building the regular code and building the unit test, though, let's say I'm running my unit test with a particular PDB file, and I'm going to read that PDB file into the unit test. That PDB file also has to get listed in the test.settings file because the unit test suite needs to copy it over and use it. So that's really important to remember. That's caused me a lot of bugs. And so to run the unit tests, you'll run from the Rosetta source directory, Python testrun.py, and give it your path to the database. That will run all of the unit tests. And then if you want to just run one unit test, you can specify -1 and myTest, where myTest is the name of the class, not the name of the file. If you specify the name of the file and they're different, it won't run. And it's good to know that each of those individual test methods that you'll define in the class, those guys run independently when you're running one suite. So the setup method will run every time before the individual test methods. And then one last thing that I want to talk about is code coverage. So when you're testing all of your code, there's a way for us to sort of figure out how much of the code base is tested. Code coverage is a cool utility because knowing how much and what parts of the code is tested is a good way to know how much of this code has this sort of insurance, how much do we know, can we catch bugs in using these different unit tests. There's a set of tools in the Rosetta code base using GCub that will determine how many lines of code are covered by your unit tests. Though, fair warning with these code coverage tools, code coverage isn't everything. You can have 100% code coverage, but if your tests aren't rigorous, it doesn't mean that much. So think about in the graph case that I talked about earlier. If I tested every line of code in my friend graph, and I only tested the case where I had one node and no connections, that only says something about that one case. It's important to not just think about, did I cover all of my code, but also, did I cover enough cases to figure out if what I have there is correct? And also, so what should you test? Good things to think about is things that are complex, things that might normally encounter a lot of different edge cases, covering all of your edge cases, classes where you might encounter data integrity issues, also error handling for bad input. If any of you have ever experienced the time where Rosetta crashed really nasty and cried, you can actually write unit tests to make sure that the right assertions are being thrown or the right exceptions are being thrown. That's a really good practice to make sure that not only does your code handle the good input that you would want it to, but also when things go wrong, it can handle it and sort of end nicely and tell the user something useful. And then also, things that are trivial. I've definitely, as a developer, I've had a lot of cases where I thought a piece of code was totally going to work, and it was really, really easy, and then there were a couple of small bugs that I wouldn't have found if I didn't write a unit test for it. Things that you want to make sure are always true. Things that you're adding to the master code base is a really good example of that. Making sure the behavior is good, and anything that ever breaks. If you find that your code has a really sort of finicky behavior, which you would hope it wouldn't, but things that might tend to break or catch edge cases frequently are things that you definitely want to include in your unit tests. And yeah, so now we're going to do a lab where you'll get some hands-on experience with the unit test suite. You'll get to write unit tests for an existing class that we'll give you. It's been shared in the Google Drive folder with you. And start thinking about edge cases for existing pieces of code. All right. Does anyone have any questions? Sure, yeah?
How do you know if you have enough cases, or you determine which cases you need Is there a specific way of determining?
So your question was, how do you know if you have enough test cases? So it really depends on what you're working with. I think the way I usually do it is if I write a method, before I write the code, I'll say, what are all of the possible cases that this will encounter? It definitely happens where, you don't think about all the edge cases and you'll find one and then you'll go back and add. I think it depends on what you're working with and just having sort of a good, solid knowledge of the requirements of what you're coding instead of just sort of coding it first and then figuring it out after. But that's definitely up to you to say, how rigorous do I want to push this?